So I will just introduce the second tutorial this afternoon. It will be made by a colleague from France, Hugues Boussard, who has worked on, I would say, agricultural landscape changes for now a few years, and on landscape modeling as well. And he has developed a plugin for QGis in order to make it possible to map the landscape connectivity. So this software is called Chloe, and I will just give the floor to Hugues. So just go on.
Thank you, Thomas. So I share. Okay, I share my screen. Everybody can see it? Can see it? Yes. Okay. So thank you, Thomas. Thank you for invited me to present Chloe Landscape Matrix plugin into QGis today. I prepared this presentation with Paul Meurice and Jacques Baudry, my colleague from the French research unit BAGAP. And it's something we are working on since a very long time. So we are happy to present it today. I will divide my presentation in 3 parts. First one is how to install technical issue plugin QGis, and but I won't be very long on that subject today. Of course, if you have issues, you can connect. You can ask us by mail today or maybe tomorrow, and so on. The second part will be about what is Chloe, what is it for, and the third step will be about how to calculate connectivity map using QGis plugin Chloe Landscape Matrix, the main subject of the presentation. I decided to make a tutorial step by step, slowly, simply, a bit complex, but in order to go together, going on and on, voilà, to be sure everything is understood. So for the installation procedure, very quickly. Just to remind you, maybe I assume you've ever done this, but so you have to download and install QGis 3.10 only, because it's not working on other software of QGis. Download and install Java GRE 1.8 minimum. You can open QGis and click on plugins, manage and install plugins. Open the zip plugin as I assume you have downloaded, and click on install plugin. Then you have to get and copy the path to your Java bin folder. For instance, for me it's C, program files, Java, GRE, blah blah blah, bin folder. And under QGis, you go here in settings, click and option. And in processing, you have providers. Here you must see Chloe Landscape Matrix. And in the path Java exe here, you have to paste the path to your bin folder and add java.exe. For example, C program file, Java, GR, blah, 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 bin java.exe. Okay, and after that you click on OK. Next thing, you have to check if you are under the Lambert 93 projection. That is the French projection, and on the project properties. And just check you have Chloe landscape metrics available on your processing toolbox like that. Today we won't see all the panel, all the functionality of Chloe, but you know, just a first step. So what is a Chloe about? What is the purpose? It's a software to analyze cover maps, like the one that can be deployed and described as it was mentioned this morning, and to express biodiversity characterization, or like Thomas said this morning, blue and green infrastructures, so BGINS infrastructures, and TVB in French. It was developed at the INRAe BAGAP since the 90s by Jacques Baudry and colleague, and it's the integration. It integrates concept of landscape ecology, such as heterogeneity, connectivity, and it has been developed by research for research in the first step for thesis. And but now we are working to put this tool available for real land planning application, and that's why we are passing our software Chloe into QGis plugin. And this has been founded by 2 French regions, Nouvelle-Aquitaine and Bretagne. And it is developed by la Fédération des chasseurs des Côtes d'Armor. So first of all, we have to have a look on the cover map. Alors, you may have downloaded a start folder with that kind of information, and so the map, the cover map, is coming from the CESBio Ozoteia plus the IGN BD Topo. So those data are very useful because they are available on all the national French sites, and freely. So it's very interesting to work with that kind of data, and it's quite precise enough. The area is about 15 kilometers by 14 kilometers. And very important, the pixel size is 5 meters in order to represent linear elements like hedgerows, like road, and so on. Here is a nomenclature of the map. You have summer crop, you have winter crop, grassland. We are working on grassland today. Hedgerows, forest, and other woods, water, urban. 3 types of road with different frequency traffic, high, middle, low frequency, and other crops. To do that in Chloe, you just have to get your start folder and get the ZI, which is the cover map, and put it here on your layers. So when you do that, you have this something like that. And first thing we have to do is just to render this a bit more realistic. Click right on the layer properties, and here you have to load a style that is in the start folder as well, cover.qml. Okay, so now you can apply. Okay, and this is the same information. 5 meters precision. Okay, you can click here to be on the whole screen. Okay, so that's what we've just done. So the principle behind Chloe is to calculate landscape metrics. It's the first thing we do with that software. We calculate landscape metric inside windows on raster map. And today, Chloe only use ASCII grid raster map .ic. And not if no other type of raster, only ASCII. And the first type of analysis we can do is, and historically is the old one, is the grid principle. And the grid principle is to split the territory using grid size. And in each grid created, you calculate a metric. And with the help of all the pixels contained in the grid. And the result of this metric, that could be, for instance, the proportion of maize, or proportion of water, or whatever. The result would be a pixel, just one pixel, on the result output. So not in the grid approach, the grid size, the window grid size, is the pixel size of the result. So to do that in Chloe, you can use in the landscape metrics here, you can use a grid panel. And let's say we are going to calculate a Shannon with a scale of 100 meters. Shannon is a Shannon diversity index, which characterizes diversity of values within the window. To do that, click on the input layer. Be sure you have clicked on the ZDA layer because it's a bug today. We really have to click on it, otherwise metrics won't be updated. So click on it, select the diversity metrics group, and select the SHDI metric. Here you can put the grid size. And the grid size is defined in pixels. So if you want a 100 meter scale approach, you have to think about your input layer. It has 5 meter resolution. So to have 100 meters scale, you have to put here 20 pixels. Okay, so it's a bit gymnastic, but voilà, 20 pixels. Let that, and here you can choose, using this button, you can choose where, the name of the output raster. Okay, so let's do that. Here, yes, ici is my panel grid. Yes, I click on the ZDA information. I choose the diversity metric. And here I choose the SHDI. Here I set 20 for 20 pixels. And here is output. I will save it to a file. I have created my own folder, you know, tuto. And here's, let's say, grid 20p, SHDI. Okay, let's run that. So now Chloe is running. It has created a grid on the whole map, and for each of the grid inside, the window grid, it's calculating the SHDI. And now you can see here the results for this metric that appears here. Okay, so let's have a try to, here. Let's calculate with 40. 40 is, the double is 200 meter scale. Okay, and don't forget here to write a new name for the output. So it's the same map, the same metric, but with a larger scale. Okay, so it's running. The time consuming in grid is not dependent from the grid size. So it will take approximately the same time. Okay. So yeah, very soon finished. Yes, here is the result. So yes, 20, 100 meters, 200 meters. Okay, I remind you. The let's have a zoom to see what's going on. So black value are value where the Shannon is least, and yellow value where the Shannon is the most. So here is, for instance, here is the Shannon is important. And when I choose 40, big pixel, yeah, not very readable. So we did that. We have something like that for the SHDI 100 meters, for 200 meters, and we can go so on with, let's say, 1,000 meters. Yes, very big pixel. So we have two issues with grid principle, and two main issues. We lose the landscape gradient, and landscape gradient is very important when you analyze landscape. We lose the continuity of landscape. It's not a smooth approach. It's very discrete approach. This is the value in this area. This is the value in this area. And the other problem is that pixel size and scale, so the analytic window grid size, are equal. So it could be very, very big at the end. So let's have a look at another principle, the sliding principle. It's another kind of analysis available in Chloe, and the principle is to displace a moving window with a displacement. By default, it's each pixel, and this window will be centered on a pixel. So it's something like that. You have a window, and you have a pixel, a central pixel here. And this window size is odd. Why it's odd? Because you have a pixel, you have a certain amount of pixel here, a certain amount of pixel, a certain amount of pixel here, plus 1 pixel. So it's odd, impair en français. And this window defined is used with a displacement. So this is one window centered on that pixel. You have the displacement, and you have this window. So in the first case, the analysis is those data, and in the other case, the analysis is analyzing those data. So there is an overlapping, and this overlapping is very useful. But let's do that on QGis. You select sliding panel, you select the same data input layer, the same diversity matrix, SHDI, and here you choose 21 this time because it's odd, and an output raster, of course. Let's do that. I choose the data information, raster input map. I choose the SHDI. Here, 21 pixel. And as output, yes, sliding 21. Okay, don't forget anything. So the first thing you have to notice is it's a bit longer. Of course, it's because of the overlapping. For each pixel, a window is centered on it. Everything is calculated. Yep, it's done to the output, and up a little displacement of 1 pixel, and it's going on and on and on and on and on in all the map. So it's a bit longer, and the more the window size will be big, and the more the time consuming will be. Okay. So we have to be patient, but we'll see it's a bit useful. Just have a look on the, okay, what's going on? Is it okay or not? It's working. It's important to understand it's a long analysis. Okay, it's finishing very soon. Okay, we have it. And this is it, the sliding window with 21 pixels. So it must be comparable to this. And maybe a zoom will tell you the story. Look the difference. So now you can see that landscape gradients, landscape continuity is back. And that is very, very useful and more readable. So we have that for 100 meters. We have that for 200 meters. We have that for 1,000 meters. And what you have to understand that is that for this part of this little zoom of the input map, which the pixel size is 5 meters. Here you have green windows. Here you have sliding windows. For the scale of 100 meters, you have here a pixel size of 100 meters, and here a pixel size of 5 meters. Here you have a pixel size of 200 meters, and here 5 meters. The same size as the input raster map. Same information, but just to be sure to understand, both grid and sliding windows output are analyzing the metric on an analytical window, both. But in one case, those windows are discrete, there is no overlapping. And in the other end, with sliding window, the overlapping can express surrounding information of surrounding one point. This is the concept. So sliding windows get the landscape gradient back. And the second advantage is that pixel size and scale with the window size are now independent. Someone has his mic. Can you? Okay, thank you. So that's the first part I wanted to show you to really understand what is sliding and what is grid, and why it is so powerful to use sliding information. So maybe Thomas, there is a question about that part, and if not, I will go on and go on the core of the subject today.
There is no question yet in the chat live. I think it's quite clear.
Okay.
Okay, there is just one question. Is it possible to use Chloe with other SRC? I think it is about projection file. For instance, to analyze map from another country.
Yes, it's possible, but it's just a little trick that when the output is generated, there is a projection file that is generated at the same time, and this one today is just the Lambert 93 projection. So you have to go and replace that file. That's the only thing you have to do. But in the future development, we will take the projection of the input raster to give it at the output. So it will be the same as your projection, your preference projection. Okay.
Okay, that's clear. Thank you.
So I go and how to characterize connectivity map. Oh, it's a good question, and it's INRAe 3-step methods. We have first to define habitat suitability map. We have to define permeability map, and note that these two steps are made in parallel, so they are totally independent. In some tools or case, you have to define the permeability map as the inverse of the habitat suitability map. It's not the case in Chloe. You can create both with their own logic. And once you have the two, you can calculate connectivity map. So that's what we are going to do. And first, of course, how to define habitat suitability map. Well, to do that, we are going to use a virtual species, an ecological model, like a butterfly. Okay, it's just an exercise, of course. So let's define the habitat of this butterfly is grasslands, but not all grassland. Only grassland which are surrounded by at least 14% of grassland in a 250 radius buffer. Okay, and the permeability will be defined as difficult to pass through woody elements. You know that type of species cannot go through, with difficulties. And the dispersion distance will be very low, like 100 meters. So let's do that. So first, define the habitat suitability map. So the sentence is grassland which are surrounded by at least 40% of grassland in a 2050 meters radius buffer. So surrounded, sliding window. It must be like an automatic reflex. And at least 40% of grassland, so the metric will be the rate of grassland. And grassland is in our nomenclature we used as the code 3. Okay, it's the code we put on the nomenclature. So we can use the Chloe metric PNV3. P is for proportion of number of value 3. And in a 250 meter radius, so the radius, so yes, we need not the radius, but we need the whole size, the diameter. So multiply by 2, 500 meters. As my pixel size is 5 meters, so 100 pixels. But the window size must be odd because sliding windows are focused on one single central pixel. So window size must be 101 pixel. So the problem is here you can notice just before we made a test with 21 pixel, it was a bit long. So now it's 101 pixel. It will be very long. So this is a Chloe trick you can deal with, is to define a larger delta of displacement, not each pixel, in order to save calculation time. And you can also interpolate approximate value for uncalculated window in order to have an output raster with the same size as the input raster. To do that, select the sliding window, select the cover map, the input cover map, of course. In the value type of matrix, put here PNV3, window size 101, and in the advanced parameter, you can choose here delta of displacement, not 1, but 10. Why 10? 10 because it's not something very very sure, but what we observe with our practical data and test is that when you choose 10% of the window size, you don't lose on the overall approach, you don't lose the landscape gradient, you don't lose information, you have approximately the same map. So 10% of someone is 10, okay, let's say 10. And you can click here to interpolate values in order to calculate windows, to interpolate values that hasn't been calculated by the analysis. Let's do that with Chloe. So here I can select sliding, the zeta. Okay, value metric. Here you have PNV3, proportion of number of value 3, the grassland. Window size 101. And in the advanced parameter here, delta of displacement 10, so every 10 pixels, and you can interpolate values. Okay, output raster. I say grassland rate 1N1. Okay, let's run that. So it's still a bit long to calculate, but it's more quick. It's quicker than if you do not set a larger delta of displacement. So here the analysis is focusing the analysis on one point, getting all data on the surrounding map, calculating the metric, and after that, not the displacement is not 1 pixel, but is 10 pixel, and so on. And all the value between have been interpolated. So yes, finishing very soon. Okay, you can close that. So here you can see a very good approximation of the rate of grassland in 250 radius buffer. Okay, so we have the cover map and we have the results. So it's not enough to define habitats, because in the sentence we also have grassland only, which are surrounded, grassland only, and 40%. And as the PNV3 metric is a normalized metric from 0 to 1, the threshold of 40% will be defined as superior to 0.4. And another Chloe trick is to use combined panel. It's just a raster calculator to combine multiple maps to a single one using an adapted formula. So you choose a combined panel here on the util, and you have here as input raster, you have to click on it and select the two which are necessary for the formula. And next here, you can click here to open the panel for the formula. And here you can see that the rate of grassland have been renamed as M1, and the cover map has been renamed as M2. And those names will be used on the formula, which is, if we have at the same time and M1 superior to 0.4 and M2 equal 3. 3 is the code of grassland in M2, so in the cover map. If we have both, so open the brace, you can say, yes, it will be an habitat. It will be an habitat. I say habitat is 1. I could say habitat is 4 or nothing or others, but I define that my habitat is 1. So, okay, it's 1, and other else, it would be 0. Let's do that on Chloe. So the combined panel is here. Here you have to click and select, okay, the grassland and the cover map. Here you have to be aware of the name of the two raster you need. And let's write the formula. If hand, open parenthesis, M1 is superior to 0.4 and M2 double equal, I said 3. Close the parenthesis 2 times, open the brace. So here I put the code of the habitat, I said 1. Close the brace, else 0. Okay, so now I can save this into habitat, grassland. Let's run that. It's something that is very it's quite quick because it's something that it's analysis that take only pixel to pixel and write an output raster with that information. So it's quick. So this is the result. Okay, so let's render this a bit more stylish. Okay. You can double click on it, or you can click right properties, go to symbology here, and here choose paletted unique values. Just click on the plus button to add one information, and here say, okay, the information I need is a 1. 1 is for habitats. And let's say the color is a wonderful green. Yes. So yes, those are habitats I wanted to describe. And if you zoom on it, you can see that not all grassland are in habitat. Only grassland that are on area where where there are enough grassland in the surrounded landscape. Okay, you see? So only grassland are selected, only in the good area. So we did that. We render the style a bit better. We have that. We have that. We have made a zoom to be sure not all grassland are in habitat. Okay, so now, second step, define a permeability map. And the permeability is defined for virtual species, the butterfly, as difficult to pass through woody elements. Okay, but what is permeability first? Permeability is how easy it is to move through a part of the landscape. Okay, so we have a landscape which is defined as a raster, so it's pixels. Okay, so how difficult is it to pass through my pixel? And I define too the friction as the exact inverse of permeability. Okay, and I speak about friction because even if in my presentation I speak about permeability map and so on, For real, it's friction map. Be aware it's the exact opposite. But anyway, it's the same concept if you inverse it. So in a pixel with a friction value n is n times more difficult to pass through. So one is unicity. It has no effect. A pixel with value of friction 1, you can go in it just like if there were no friction. Large values are pixels difficult to pass through, or even barriers if you put a large value of friction. And 0 can be defined as corridor. So 0 is a pixel that don't take you any force, any difficulty to pass through. So to do that, the permeability map, to define it, we have to translate. It's a proposal, of course, but it could be a translate of the cover map, the input cover map we used, to a friction map. And this friction map is defined in the friction.txt file in the start folder. And I put this. I put summer and winter crop as 1, so butterfly will pass with no problem. Grassland are corridors. Hedgerows, forest, and other wood elements have 10 value. It's even stronger, 10 values. It's 10 times more difficult to pass. Water 1, okay, can go. Urban and road high frequency, it's difficult to pass. Middle frequency, a bit less, but it's still difficult to pass. Road with low frequency, okay, you can pass. And other crop, I put a middle value. So to do that, to create that kind of permeability map, that is the exact translation of another map, and in that case, the input cover map. A clever trick is to use search and replace panel to replace values on a raster. So to do that, open the search and replace panel, select the ZDA cover information, and open with that button, go and choose the friction.txt file. Once you have that, you can read values from input ASCII, which will update the values here, which are the value of the nomenclature. Select the friction that is available in the friction.txt and apply CSV map to update the new values. Okay, let's do that. Search and replace, the input map, the CSV file. Here, by default, it's only CSV. So to see TXT, click on TXT. And it's not here, of course, it's here. Friction.txt. Okay. Read values from the input ASCII. So this reads the values here and put them here. So select the friction value, friction column, and apply CSV. Okay. Everything is updated. So now I can save this to a file and set permeability grassland, for instance. Let's run that. As combined panel, it's quick because it's only a pixel to pixel analysis. Okay, I have it. But let's rendering it a bit more practical. Here you can select palette unit values, random color you can choose, for instance, magma, and invert the color ramp and classify values. So 0 value will be yellow, and strong value of permeability will be black. Of friction, excuse me, of friction will be black. So the permeability is the exact opposite. So here I have high value of permeability, low value of permeability, low value of friction, high value of friction. But let's speak about permeability. Okay, I can have a zoom on it just to see what is going on. Okay, so it's really a translation of my input cover map, just a translation. Okay, so we did that. We have the permeability map, and we zoom on it. So now we can calculate a connectivity map, because we have habitat in one hand, you have permeability map in other hand. So now we can calculate connectivity map. And the Chloe trick is to use a distance panel to do that, in order to calculate a functional distance panel, a functional distance, excuse me, in order to characterize connectivity over habitats in landscape. The principle is to create a functional distance map as each pixel of the output raster is characterized by the least cost path distance from the nearest habitat according to permeability to friction map. Okay. So to do that, choose here the distance panel. Here, this time don't use Zeta, but use the habitat we calculated before. Here you have to put the value of habitat that are in this map. So I said one value, so it's 1. And here in distance type, don't use Euclidean distance, but functional distance to take into account permeability we define. In the friction file, you can here select and put the permeability we have created. Do not, at the moment, do not use the maximum distance. Let's this like this, and select an output raster, an output as QGis. Okay, let's do that. Distance panel, habitat is input, and my value of interest in the input raster is 1. I choose the functional distance, and here I go and select my permeability that we have just created. Yes, this one. I let this like that, and here I say connectivity grassland. Okay, let's run that. So here the calculation is kind of diffusion from habitat, and according to permeability, it will give a value to all pixels. What is the distance for this pixel to the nearest habitat according to the permeability? Okay, finishing very soon. Yes. Okay, and this is the result. Not very beautiful, but this is the result. And if you go here to select to view the values of the map and click anyone here, for instance, you have 135. So the pixel I click is 135 equivalent meters to an habitat. So to view this more readable, click here on the properties, and in the symbology, you can choose single band pseudo colors. And here you have the minimum value you want to take into account. And here you have the maximum value you want to take into account. So let's say 100, because we said that our butterfly can disperse to only 100 meters. And in the color ramp, green is good, it's a good ramp, but just invert it to have a value close to habitat very green, and the more you go and go from the habitat, the more white you are. And let's say that large values of distance are not white but transparent. Okay, transparent here. Apply that, and this is the result. This is the distance information we can calculate with Chloe using this habitat and using this permeability map. So, okay, I put the layer of the habitat too. So to me, it's not satisfying, and to us, I'm sure for you too. Too few habitats are connected, and we know from observation that this is not accurate enough. There is a flaw in the model. This is a wrong model. We cannot see here any connectivity, any corridors, any connectivity. So no, it's not the good. We have something. We have a problem with the hypothesis, and especially we have to refine the hypothesis according to the permeability map. So we said permeability difficult to pass through woody elements, but can we say that woody element can be corridors because there are grassy strips along woody elements? Okay, butterfly cannot go with difficulties passing through woody elements, but there are here grassy strips that can be used for species like butterfly to go and go. So what if we say yes, we can go further and update the permeability map, and in that case, and except where there are roads or where there are urban areas. Okay, let's say that. And to do that, so we have the objective is to put a zero friction, corridor friction, to code a code to pixel close to woody element, but not on woody element, of course, and not on urban, road high frequency or road middle frequency pixel, in order to express new corridors in the permeability. To do that, we have two solutions at least. Solution one is using the distance panel to woody element, but let's use the solution two using a square sliding windows, very little one, 3 by 3, which calculates the proportion of woody element. Okay. So to do that, the first step is to create an alternative cover map. In order to group woody elements, hedgerow, forest, other wood will be redefined as wood, and to group urban, road high frequency, road middle frequency, 8, 9, and 10, that will be refined as urban and road. And to do that, once again, use the search and replace panel. So you take the search and replace panel, you take the Zeta cover information, and here you have to click on read values from inputs ASCII in order to update values. And here you can put new values for the old values you want to change. Values that won't be updated won't change. So for instance, water 7 will stay water. Okay, let's do that. Search and replace panel, Zeta cover map. I read the values from the cover map. They arrive here. And let's say, okay, so I say 4, 5, and 6 become 4. And 8, 9, and 10 become 9. Become 8, excuse me. The output cluster ASCII is, well, let's say, Zeta alternative. Yes. And I run that. So now the analysis is creating a new cover map in order to be able to calculate a new thing on it. Okay, so we have this one, and just to be comparable with the old one, you just have to click right, properties, and style, and go and load the style I put in the start folder, cover alternative. Okay, apply that, and now here you can see the new nomenclature. So this is it's not a new cover map, but it's a cover map we are going to use now. Okay, so next step is to detect local wood. Yes, we want to know where there is wood not far from here. So in order to create those edges. So to do that, use a sliding window. Select the alternative this time, and select the proportion of woody elements. So now it's not 3, it's 4. The 4 code in the nomenclature, PNV4, and this in a very little window, 3 by 3. And in the advanced parameter, we have to choose a square window shape, because by default Chloe uses circular windows. So now, in order to integrate not only cardinal neighbors of pixel, but also diagonal neighbors, you have to select a square shape window. Let's do that. Sliding window, c'est the alternative. Be sure you click on it. Select value metric, and here the proportion of number value 4 for my woody elements. Window size 3, it's okay. And in the advanced parameter, select square window. Okay, so my input raster will be, let's say, local wood. Run that. Sliding window with 3 by 3 windows. It's not a huge window, so it's quite quick. Do not make a displacement here. Let the displacement of delta of displacement to 1, because here we really need to have information, very precise, very accurate information for each pixel. Do I have a wood in my local information, in my local window? Okay, it's very important to not have a displacement here. Okay. So this is a local wood, just a detection of wood elements. Huh? You can see it. Okay. So, yes. So the third step now is to combine information to update the permeability map, a new permeability map, for taking into account local wood edges. Okay. So to do that, it's a combine panel. A combine panel which use the local wood we just created, the old grassland permeability, and the new cover alternative. So you have to check those maps. To select the formula, you have to click on here, and here, be very careful of the rename of your file, because it's not if you displace here the order of the different raster, you will have here a different naming. So be very careful on the naming, and do not apply the formula like it is. No, very be careful of the naming. So now we have M1 for the local wood, M2 for the grassland permeability, the old one, and M3 for the cover map. And the formula here is if we have at the same time the local wood superior to 0, so we have wood in the surrounding space, and the cover is not exclamation point equal means not. So cover map is not wood, and cover map is not 8. You know, it's urban and road. So you will put the code 0 to explain corridors on the new permeability map. So it will be a corridor. It will be 0. Otherwise, it will be the old permeability value. Just to click M2 because it's M2 permeability here. Okay, let's do that on Chloe. So I use combine panel. I select the old permeability. I select the local wood. I'll select the Zeta alternative. I here go and see the naming is not the same here. You see? So if we have hand local wood superior to 0, the cover map M3 exclamation point equal 4, it's not a woody element, and M3 exclamation point equal 8, it's not urban and road pixel. Close the parentheses, close the parentheses, open the brace. This will be 0 code. This will be corridor, new corridor pixels. Else, just put not M2, M1. Just put the old permeability map. Okay, so now I have to save this to my new permeability. Let's say permeability alternative grassland. Okay, run that.
Okay, while you are processing your operation here, there is a question from Selena, and she's asking, how do you parameterize habitat suitability or quality if you don't have to focus on a particular species?
It's a difficult question. I remind you, I'm just a software engineer, and my purpose is to bring you some tools to manage your data and your hypothesis with your ecological model. So as far as I know it's possible to have what we call in French espèce parapluie, species that represent a larger group of species. So if we model this species, you can say by boule de neige, you can say that other species are also imply in that compartment. But if you have two species very precisely defined as completely different, you have to define habitat, define permeability, and so connectivity separately for the two species. Okay, and maybe after you can see where it's relevant for one species, where it's not for the other, and maybe you have some space on the territory where the two species are present, and other space where other area where there's just one and not the other, and so on. Okay.
Okay, and maybe you won't show us how to combine this kind of two collectivity map, for instance, but I think you may have already think about how to proceed and to combine this kind of multi-species analysis. Am I correct?
Yes, but it will be very hard to precise this today, because
Okay.
I need some more material to show you something like that, and I just encourage you to contact me after.
Okay, so Chloe does that, but it is not in this practical.
No,
Okay,
I'm sorry for today.
No, it's okay. Don't worry.
So here we have the new permeability map we've just generated. Just for the rendering, we have the old rendering of the old permeability. Just click on it, style, copy style, and you can click on the new permeability, style, paste style. So now you can really compare them with the same style. So if you zoom on it, yes, you can see what happened. You can see that woody elements have been surrounded by a corridor, but not on roady elements or urban elements. Okay, it's exactly what we wanted. So now, yes, we have that. So now we just have to calculate a new connectivity map, taking into account this new permeability map. Okay, so the distance panel. You can click on habitat grassland. The habitat is the input layer. Okay, remember that. One value is the value of habitat. You type the functional distance. You put here. You set the new permeability map we just created here, and this will be the new continuity, the new connectivity map for today. So it's a distance panel. Habitat grassland, one value for habitat, functional type distance. The friction is the new permeability alternative grassland. Yes, this one. And the output is connectivity alternative, let's say. Run that. So once again, each pixel will be characterized by its least cost path distance to the nearest habitat according to the new permeability map. Okay. Okay. So it's as beautiful as it was, and select the old connectivity. Click right, style, copy style, and now on the new one, style, paste style, and now is a connectivity. The connectivity that could be very more interesting than the old one, because here you can see with 5 meters of precision that there is corridors through landscapes. So that was the main purpose of the presentation today, but we can go further with that kind of analysis, and there's just one step I wanted to show you today. Just one step further. So yes, habitat are now connected through landscape element. So I don't know if it is a good model. Again, I'm just a software engineer, but the tool allowed you to test and set value parameters, data. Of course, if you change your cover map, you will change the result as well. So you have to test and be careful of all your parameters. And just what Chloe is about is to help you to view the results. Okay. So for instance, here, if now I don't say, oh no, my species don't go from 0 to 100 meters, but only, let's say, 17 meters. Yes. So same artifact, okay, apply. Oh yes, it's more like that because I know that here and here it's not connected and so on. You can have something like that as an approach to precise what kind of connectivity you want to characterize. But anyway, sorry. Yes, it's okay. So let's start for today. How habitats are clustered. So now we have habitats and a connectivity map, but we don't know, for now, we don't know who is connected with who, which are habitats that are in the same clusters, in the same aggregate. So what is the cluster panel about? So here you have to select the habitat. It's exactly the same parameter as the distance panel. You have to select the habitat grassland here, select the one value of the habitat, select the functional distance, put here the permeability, like for the distance, like for the connectivity. But here you have to put the maximum, the threshold. So here you have to put 100 meters if you want to test 100 meters. You can put a minimal area for clusters, let's say 0. And here you can put the output raster. It will be the last step for today, but I think it's interesting to see what it gives. Okay, functional distance in meter, 100. The friction is a permeability alternative, the last one we generated. Minimal area 0, and the output raster, let's say cluster grassland. So now it's calculated which cluster are which habitat are together according to the permeability. Okay. Okay. Wonderful, isn't it? So to render it more beautiful, paletted unique values, classify values, and delete the 0, 1 because it's the background of the landscape. Apply that, and here you have the clusters of the landscape. So if there is the same color, it's the same cluster. So all habitats in let's say pink are connected together with at least one pass. The green one are together. Here they are together, and so on. So here was the final information I wanted to show you for today. So you can really express some very precise connectivity information and with a precision of 5 meters.
Okay. So thank you, Hugues. There is a question I think it is related to other application of connectivity calculation. Axel is wondering if there is an option in Chloe to calculate graph theory-based metrics, such as the probability of connectivity.
No. The graph theory is not in Chloe. Okay. Because we have a different approach. There is two things. First of all, I think the graph theory can be viewed as the next step of that kind of information, because here you focused on which are the habitats and how they are connected. So you can set a value of the node between the arc in the graph theory. Okay. And in the other end, we have ever work on the different approach of is in my aggregate, in my cluster, are habitats really strongly connected or not? Which habitats are more connected than the others? So and so on. So we have begun to work on that kind of calculation, and it's not available in Chloe yet.
Okay, thank you for your answer. I think your Chloe software is pretty nice, even if you are mentioning that you are not working on specific species or so on. But I think it is really user-friendly in order to make some very concrete maps that are meaningful for stakeholders. And I think it is in the line with what Jose has shown to everyone this morning about the use of this kind of map afterwards with decision makers. So I think it is really interesting to see where are the clusters, the size of these clusters. These are some small and disconnected or connected clusters together as well. And no, I think it is really efficient. And well, it was the aim of this tutorial in order to make people able to use directly software on their own, and then maybe to go further into detail and try to combine different umbrella species or multi-species analysis like this one. And of course, if some of you are interested to go so far, please contact Hugues. He will be happy to help you in this use of Chloe software. There are still times for questions if some of you are wondering other questions. But anyway, Hugues, they are just thank you for they do thank you for your talk, because it was clear, I think, very practical. So there is a question. Someone she's wondering if there is a list of papers that is using your software yet.
I don't have the list, but there are some theses that use a Chloe approach, sliding approach. No, I don't have the list, but I think Jacques Baudry, my colleague, can give you such a list. And last thing I wanted to say, because my other colleague Paul wanted me to say that, is we are still working on that software, and we are still developing some new algorithm and new concept. And for instance, we are working on the landscape of eco-landscape. We are developing, we are redeveloping the sliding window software algorithm in order to be very more fast, and so on.